On the morning of September 1st, 1859, English astronomer Richard Carrington was sketching sunspots through dark filters. Around 11 a.m., he saw a sudden flash of intense white light from the area of the sunspots. The whole event lasted 5 minutes. But what followed about 17 hours later was even more remarkable. The Earth's magnetic field trembled as a massive solar storm hit our planet. This wasn't just any storm, it was a geomagnetic storm so strong that telegraph systems across Europe and North America went haywire. Operators received shocks, and machines worked even when unplugged. Auroras, usually seen in polar regions, dazzled skies as far south as Cuba and Hawaii, turning night into day. According to NOAA, gold miners in the Rocky Mountains woke up and made coffee, bacon, and eggs at 1 a.m., thinking the sun had risen on a cloudy morning. This event, now known as the Carrington event, was the most powerful geomagnetic storm in recorded history, hinting at the sun's hidden power and showing us how vulnerable our world is to its celestial moods. Fast forward to today, 15 solar cycles later, and we stand on the brink of another solar spectacle, the upcoming premature solar maximum and the reversal of the sun's magnetic field. As the sun approaches the phase of its peak activity in its 11-year cycle, it promises increased solar flares, sunspots, and coronal mass ejections. While we marvel at the potential for beautiful auroral displays, there's concern for our technologically dependent society, its impact on our health, and the warming of the oceans. The maximum also comes at a time around the Artemis mission, humanity's return to the moon after more than half a century. So, what will the upcoming solar maximum do to our planet in the coming months? What are the anomalies in this solar cycle that NASA is concerned about? Finally, and most importantly, will the upcoming phase of the sun's activity risk the life of the astronauts of the Artemis mission on the moon? Everything on Earth owes its existence to the sun. As our primary energy source, the sun might look the same every day from our vantage point, rising in the morning and setting at night, a cycle that has been constant throughout human history. Yet, up close, the sun is a dynamic ball of plasma. It's covered in sunspots, flares, and other features like prominences and filaments that can outsize our planet. Essentially, the sun is a massive ball of hot gas that's always changing. But this change follows a pattern. On average, every 11 years, the sun undergoes a cycle of increased and decreased activity known as the solar cycle or Schwabe cycle. We are currently observing the 25th cycle of such activity since systematic records began in 1755. But how did scientists notice the sun's activity changes over time? The key to this discovery lies in sunspots. Sunspots are temporary dark areas on the sun's surface, looking darker because they are cooler than the surrounding areas. The temperature in the center of a sunspot is between 300 and 4500 Kelvin, much cooler compared to the surrounding area's temperature of about 5800 Kelvin. They are caused by intense magnetic activity and sometimes can be as big as Earth. When astronomers started to keep track of these sunspots regularly, they noticed a fascinating pattern. The number of sunspots went up and down over a cycle of about 11 years. They also observed changes in the size of sunspots, the area they covered on the sun, and where they were located. A solar cycle starts with a few sunspots, known as the solar minimum. Then, as more sunspots appear, it reaches a peak called the solar maximum. After this peak, the number of sunspots begins to drop, marking the end of the cycle. Another interesting pattern is where the sunspots appear. At the beginning of a cycle, sunspots show up at mid-latitudes on the Sun. As the cycle progresses, they move closer to the equator. This movement creates a pattern that looks like a butterfly when plotted on a graph called the butterfly diagram. This diagram is a great way to visualize the solar cycle's regular pattern. For a long time, astronomers kept a record of solar activity by observing the behavior of sunspots alone. But as technology improved, they noticed two more things that changed over a solar cycle. The first was the solar magnetic field. The Sun is a giant magnet with a north and a south pole. The Sun's magnetism lies at the heart of its dynamic features. Astronomers found that the magnetic field goes through a complete reversal of polarity with each solar cycle. This means that the solar magnetic north becomes south, and the south becomes north. The pole reversal occurs around a solar maximum, marking the end of the maximum and the transition of the cycle to its minimum, and importantly, marking the cycle's midpoint. This phenomenon remains one of the most intriguing unsolved problems in solar physics, as we still don't understand why the magnetic field reverses polarity throughout the solar cycle. While the reason for polarity reversal remains a mystery, one feature of the Sun may be playing a major role in this. The Sun rotates in a non-uniform fashion, spinning at different speeds at different latitudes. At the poles, it rotates slower than at the equator. This is called differential rotation. It is believed that the Sun's rapid differential rotation causes the plasma to drag magnetic field lines around, causing them to get tangled and twisted as they eventually reach the surface and create sunspots. Sunspots and other instabilities weaken the field lines even more, reducing them to zero and giving them a chance to rearrange and reappear at the poles with opposite polarity. Even though polarity reversal is a regular and predictable event, it remains one of the most intriguing unsolved problems in solar physics. Another aspect of the Sun that changes with the solar cycle is its overall activity, including solar wind, solar flares, and coronal mass ejections. This activity reaches its highest point at the solar maximum and its lowest at the solar minimum. Because of these findings, monitoring solar cycles now involves looking at solar activity and polarity reversal, in addition to counting sunspots. The current solar cycle is proving to be more intense than previously anticipated and is reaching its peak earlier than expected. When this cycle began in December 2019, forecasts predicted a peak in July 2025 with around 115 sunspots. However, the NOAA Space Weather Prediction Center has updated its prediction, now expecting the peak between January and October 2024, with an estimated 137 to 173 sunspots. This change in prediction underscores the dynamic nature of solar activity and its inherent unpredictability. Understanding the consequences of this increased intensity and early peak requires a closer look at X-class solar flares. Solar flares are powerful bursts of electromagnetic radiation from the Sun's atmosphere triggered by the reconnection of strong magnetic fields. Flares are ranked by their strength. B class is the smallest, followed by C, M, and then X, the most intense. C-class flares are generally too weak to affect Earth significantly. However, M-class flares can cause short-term radio blackouts at the poles and minor radiation storms, posing potential risks to astronauts. Each class is further divided into a scale from 1 to 9. The Carrington event in 1859 was associated with an X-class flare. Since the current solar cycle started, the first X-class solar flare occurred on July 3, 2021, leading to a substantial radio blackout. High solar activity can potentially impact NASA's Artemis missions to the Moon. The guidelines for the Artemis mission are clear: launches should steer clear of times close to solar storms. This caution is due to the energetic particles from solar storms that can harm electronic circuits and disrupt radio communication, which may make it difficult or even impossible to stay in contact with the spacecraft. On a more positive note, the solar maximum phase increases auroras, known as the Northern Lights or Aurora Borealis. These are stunning light displays created when the solar wind's charged particles collide with molecules in Earth's atmosphere. So, as we prepare for the solar maximum, it reminds us that we are just a small part of a much bigger universe. It's a chance to reflect on our advancements and vulnerabilities, encouraging us to look beyond our daily lives and consider the bigger, cosmic picture that connects us all.